Hello everyone, I am Prashant Chaudhary and welcome to the presentation on the topic multiplayer games in AI. So as we know, AI has continued to improve with aim set on a play, which is being unable to tell the difference between a computer and a human player. So in multiplayer games, artificial intelligence is used to generate responsive, adaptive, or intelligent behavior similar to human-like intelligence, and it also uses searching algorithms and logics. So the concept of multiplayer game. So the multiplayer game is a game playing approach which is a search problem defined by some initial state, some successor function, a goal state, and a path state. So initial state is where we have to start the game from, which is that is the start state, and the successor function is the function which determines our next step, the next state from the present state, which is where we have to go next. And goal state is where we need to reach finally, which is the destination state. And path cost is what is the complete cost of reaching goal state from the initial state or start state. And it also obeys some of the rules of the game, and also it is able to find the path. It is also able to make the decision, and it is also able to make the planning for the game. So AI uses all those things which a natural human being can use. So next slide is where is the AI from where is the AI for managing multi-party interaction? So it could be in team versus team. AI could be in one of the teams, and other teams could be also AI or the human players. And it could be player versus player versus player. So we have multiple single players, and it could be in MMO, which is massive multiplayer online games. So which is basically a social game, social networking game, and it also can be in board games negotiation. So negotiation games explicitly involve and encourage making deals and alliances with other players and backstabbing when needed or appropriate. So it is basically a diplomatic game kind of thing. Mm, Next thing is, how does AI interface with player communities? So it could be a long-term rival or buddy of yours. So it could be one of the rivals of any player, or it could be one of the buddies. And other thing is, it could be in one of the teams. So it can make guilds or teams with humans or other AI system. And forum, which is assembly or conference. AI is able to do that also. Next thing is type of multiplayer game. So first of that is perfect information game. So perfect information game could be an player game, and it has and here all the players have complete information of the game, and the end of the game could be a win for any of the players, or a lose for any of the players, or a draw. And here state configuration is defined, which is every state configuration of the perfect information game is well defined, and also the state space, that is the transformation rules, are also defined. Next thing is, for example, we have in perfect information game chess or checkers, where we have two players, or for ancient chess in India we had four players also. So this is a type of multiplayer game, and we have a definite rules, a set of rules, transformation rules, and also the state configuration is very defined. The other one is imperfect information game, and in that uh, we don't have uh, we don't have perfect information, like every player does not have the complete information of the game. For example, take bridge game or card game. So in card game we see that only the cards are known to the individual players only, and not to all of them. Like they have their own set of cards, and they know only their cards and not all the cards. And here we see that they can only guess what others player have, and the outcome is not fixed also in this. And the other type of game is probabilistic game. So in probabilistic games, for example, let's say Ludo. So here every move is not deterministic, and the outcome is totally based on chance or luck. For example, in case of Ludo, if a die is rolled out and we get 1 to 6 and 1 to 6 any of the faces, and something will happen, we get something, and based on this the number of moves can be made. So we don't know the outcome, and it is totally based on chance, and Ludo is one such perfect example of that. So that was all.
Hello. The field of multiplayer games is fastly developing with new research and experiments conducted each day, and the applications are tremendous. Here, I will discuss about the prominent algorithms that are used in this field, and I will do a comparison of advantages and disadvantages between them and where they are useful. So first, let's start with the two algorithms, Max-Parent and Paranoid algorithm. The Max-Parent algorithm is the most simplest and common technique used often. It is simply an extension of the alpha-beta search technique but to the multiplayer games. What happens is that in the game search tree, each player will be awarded a payoff, and the root player will be choosing the child with the highest payoff. So this algorithm has proven to be successful, but there are certain problems and limitations associated with that. We can say that the problem of Max-Parent algorithm is twofold. First one, the problem of pruning. Compared to the alpha-beta search, less pruning is possible. So because of this, we have a very limited look ahead. At the extreme case, the pruning is possible if there is a lower bound on each player's score and an upper bound on the sum of score. Even then, only basic shallow pruning is possible. So while this is a major disadvantage, and the second disadvantage is that often the Max-Parent algorithm is too optimistic. The underlying assumption that no other players or opponents have a coalition formed against the root player is often not the reality. That gives the Maxen algorithm the limitation of being too optimistic. So because of these two major problems, the other algorithms were introduced to overcome them. So one such algorithm is the paranoid algorithm. So paranoid algorithm is basically effort to solve all the limitations of the Max-Parent algorithm. Here, the concept is to reduce the multiplayer game to a two-player game by making that the situation is paranoid. That is, every other opponent player has formed coalition against the root player. Uh, why did they introduce this? Here, because of this, alpha beta regular pruning is possible. It gives us a larger search depth, and it has outperformed Max-Parent algorithm in many cases, especially in games like Chinese checkers and hearts. Also, at the same amount of time, deeper searches are also possible. So, because of all these advantages, we often use paranoid algorithm and Maxwell algorithm, but still, it is not the best algorithm because it has its own limitations. The limitations being that because of this incorrect assumption that or every time all the other opponents are forming coalition against the root player, the player might become too defensive and other favorable moves of players are not considered. And often other players may dominate the root player in case of deep search. So to overcome the combined limitations of Max-Parent and mainly paranoid algorithm, researchers introduced a new algorithm called best reply search. It was introduced in 2011 by scientist Gordon Weinert. This mainly focuses to overcome the limitation of paranoid. It is very similar to paranoid algorithm, but there is a root difference. The root difference being that instead of the traditional search methods where every player will be allowed to make a move, resulting in large search trees, but here only the opponent player with the strongest move against the root player is allowed to make a move. At a mid node, all the moves for the opponents will be searched. It means that an opponent is allowed to make a move even if it is not its turn. At the following max node, it will again be the root player's turn. So because of this, it converts the multiplayer game into a two-player game. What are the advantages we get by this? Because of this technique, more number of max nodes are visited and investigated. This gives us a large look ahead compared to the paranoid algorithm. Also, alpha beta search pruning is possible here, which gives a significant advantage over the max n algorithm. And a max n and the paranoid algorithm have these unrealistic assumptions which are ignored or successfully neglected here in the BRS algorithm. Also, experiments were conducted here and it has proved to be successful in many cases, which will be discussed later in this video. The main disadvantages included in this method is that we are not allowing all the players to make a move. This will lead to illegal positions. Also, the players or opponents whose moves may be favorable to the root player are still not considered. Thank you.
Hello, this is Prashant Sachan, 19MA40012. I will explain the algorithm part. First of all, we will discuss the Maxent algorithm. So, the Maxent algorithm can be used in the game with any number of players. At a leaf node, an n tuple is generated, where n is the number of players, and every entry corresponds to the score a player receives. So, at internal node, a player chooses the child with the highest score for the player. You can see in the figure. Note A, B, and C internal nodes, and node A, player 1 is to move. In node B and C, player 2 is to move, and player 2 has the choice between 626 and 416. So in node B and choose 626 to maximize the own score. So in node C, both options are equally good for the player 2. In this example, the left child is chosen and node C get value 729. Player 1 now prefer node C above the node B because it gives a higher score for player 1. So in multiplayer game there may exist multiple equilibrium points. So it has been proven that max and compute one equilibrium point. Furthermore, if tie-breaking rule is altered, it may be arbitrarily affect the max and value of the tree. So we demonstrate this changing the tiebreaker rule in this given figure, and instead choosing the leftmost child in case of tie. Now the policy is to use the child which has the lowest value for the root player is chosen. So in this case, node C has the value 5 to 1. So this implies that player 1 prefers node B over node C, and node A has value 6 to 6 instead of 7 to 9. Okay, so now paranoid algorithm. The paranoid algorithm reduces the multiplayer game to a two-player game by making the paranoid assumption. The algorithm assumes that all opponents have formed a coalition against the root player. So by doing so, regular alpha beta pruning is possible. So this leads to a larger search depth. In this figure, you can see it is the same tree as in the last figure. So but now the leaf node are evaluated in a parallel way. So here the sum of the evaluation score of player 2 and 3 subtract from the evaluation score of player 1. A second possibility is that player 2 and 3 ignore their own score and only minimize player 1 score. So in node B, the right child is preferred the value -3 after finding -4. as the value of first child of node C. So all the remaining children can be safely pruned according to the standard alpha beta rule. The root node A receive minus value minus 2 receive value minus 3. Now best reply search. So uh, the traditional search method allow every player to make a move, resulting in the large search tree in BRS, that is best reply search. Not every opponent is allowed to make a move. Only the opponent with the strongest move against the root player may move. So at a min node, all move for the opponent are searched. So it means that opponent is allowed to make a move even it has not its turn. So at the following max node, it is again the root player turn. BRS achieves the long-term planning because more max node are visited along the search path. So while being at the same time less paranoid. So when iterative deepening is applied in BRS, a min node always contains all players. So when comparing this to the standard search depth of the paranoid algorithm, the search depth increase irregularity. For instance, with 4 players, the search depth of BRS is increased to the depth 1, 4, 5, 8, 9 each. So with respect to the standard depth, you can see the figure. Node B and node C are labeled 2, 3, which represent one of the opponent. That is a player 2 that is player 2 or 3. So is allowed to make a counter move. So the labels near the edge underneath node B and C indicate which player move is played. So at the next play, it is again player 1 turns to play. So node B assign the value to, because player 3 has the strongest counter move. When searching the first child of node C, which is a move by player 2, a regular alpha beta pruning occurs. So in this case, the remaining move of player 2 and all move of player 3 are pruned. Thank you.
Hello everyone. As we have seen some of the prominent algorithms in the field of multiplayer games like Maxent, Paranoid and Best Reply Search, now let's compare these algorithms and check which algorithms perform better when they are played against each other. Now to conduct an experiment, we have chosen Chinese checkers board game. To give the basic introduction of Chinese checkers board game, it is a star-shaped board game that can be played by 2 to 6 players. And the instructions or rules are as follows. The main initially a player is given with 6 pieces and a base, a triangular shaped base, and the goal of each player is to move all of his 6 players to the opposite side base or called home base. Now each piece may move to an adjacent square or they may jump over another piece to an empty field, and a player may also make multiple jumps with one piece in one turn. So the first player who manages to fill the home base, that is the opposite side of his initial base, wins the game. And this is the initial picture of a 3-player Chinese checkers game board. So here each player is given with initial base and their 6 pieces, and the goal is to reach the opposite side of the board, and the first player who manages to do that is considered as the winner. Now it is also given that to avoid blocking behavior, the player wins the game when the home base is filled and the player owns at least one of his pieces in the home base. That is, a player can block the opponent's home base by keeping his piece. So to avoid that blocking behavior, it is considered that if the home base is filled and at least one of the piece is considered is of the player, then he is considered as the winner. Now a 3-player Chinese checker game board experiment is conducted, and the 3 players were given as algorithms like BRS, Paranoid and Maxent, and the results were recorded. So according to the results, Here time parameter is nothing but time given for each move. Like in the first case, for each move we have given 250 milliseconds, and in second case 1000 milliseconds, and in the third case it's 5000 milliseconds. And in each case BRS has a win ratio more than 55%, or accurately saying on an average 60% win ratio is 60% of the games was won by BRS. So we can clearly see that BRS is significantly stronger than Paranoid and Maxent algorithm. So to compare BRS against Maxent and Paranoid, we have also conducted an experiment solely against BRS versus Maxent and BRS versus Paranoid, and both results were recorded. Now, for seeing BRS versus Maxent algorithm, when in the case of 3-player, 4-player, and 6-player, and in given respective times for each move, in every case almost BRS has a win ratio between 72 to 88%. That solely says that BRS is much stronger than Maxent algorithm and always performs better than Maxent algorithm. And when BRS versus Paranoid is compared, in each case BRS has a win ratio of 58 to 76%. That is, on an average 60% of the games were won by BRS. So on a conclusion, we can say that BRS was able to win almost 60% of games across all experiments, whether the opponent is Maxent or Paranoid. So by this we can say that BRS is the strongest algorithm in the Chinese checkers. Not only in this game, but research shows that BRS is significantly better in maximum deterministic multiplayer games. So this is all about the deterministic multiplayer games and their search algorithms. These were the presenters of the video. Thank you.